Welcome to the next video lecture on strength of materials. Next problem is like this. A hollow shaft transmits 200 kilowatt power at 150 rpm. The total angle of twist in a length of 5 meter is 3 degree. Find the inner and outer diameters of the shaft if the permissible shear stress is 60 megapascal. Take G is equal to 80 gigapascal.
Power P 200 kilowatt and speed 150 rpm. Length of the shaft is 5 meter. Angle of twist is limited to 3 degree. Is 3 pi by 180 radian. Shear stress is 60 megapascal and G is 80 gigapascal. This is the given data. Whenever power and speed is given, first step you need to carry out is torque calculation. So let us try to calculate the torque first. So we have the equation P is equal to 2 pi nt by 60,000. So P is 200 is equal to 2 pi, N is 150 into T is a mean torque divided by 60,000. So this gives you a torque of 12.732 into 10 power 6 Newton millimeter. Initially you will get it in Newton meter. Again you convert into Newton millimeter by multiplying it with 10 power 3. So that's how you get this. First let us use strength criterion. Based on strength criterion, we have P by J, torque by polar moment of the shaft, equal to maximum shear stress divided by radius of the shaft. Now this is a hollow shaft, so R becomes R naught. So I'll substitute all the values now. 12.732 into 10 power 6 divided by J is in terms of D naught and Di, but both are unknown here. Let us keep them as it is. So pi into D naught power 4 minus Di power 4 divided by 32, which is equal to tau. Tau is given as 60 divided by R naught is D naught pi 2. Okay, D naught and Di both are unknown here. This is one of the equation which you can simplify. Pi by 32 D naught power 4 minus Di power 4 into 60 is equal to D naught by 2 into 12.732 into 10 power 6. This 60 I'll send it to right side. So divided by 60 I'll call this as equation 1. Because I cannot further simplify this. We don't know the relationship between Di and D naught. So we cannot do anything more than this. We'll keep it as it is. Second, based on rigidity criterion, we have T by J is equal to T theta by L. This is the rigidity criterion. Substituting the torque and J, this is J, is equal to G, 80 into 10 power 3 into theta, 3 pi by 180 divided by L. L is 5000. From this also I can separate pi by 32 into D naught power 4 minus Di power 4 is equal to 12.732 into 10 power 6 into 5000 divided by 80 into 10 power 3 into 3 pi by 180. This is equation 2. Here also we cannot do anything more than this because DO and Di both are unknown here. Now you observe, unless we combine these two criterion, equation 1 and equation 2, if we don't combine them, we cannot get the solution. Since both the criterion are to be satisfied, we can combine these two equations. We observe equation 1 and equation 2 has the same left hand side. LHS is same. So RHS can be equated. We equate these two and find out D naught. Directly you will get D naught from this. So D naught will be obtained as 143.24 mm. When you solve these two equations, you will get the outer diameter. And to get the inner diameter, you substitute this D naught into any one of these two equations. Using this in, I am not going to do that. I hope you will be able to do that easily. You should get a Di of 127.73 mm. We go to next one. Observe this. This is a shaft with sections A, B, C, D. It's a 60 mm diameter shaft subjected to torque at various sections as shown. Determine the total angle of twist, maximum shear stress in each portion, angle of twist in each portion, taking G is equal to 8 in 10 power 4 megapascal. When you have more than one different torque in a shaft, then you will have to see effectively how much torque is applied or acting at each portion. For example, in AB portion AB is subjected to some torque. Between BC, again, there'll be some other effective torque. Between CD, there'll be some other effective torque. Okay, that we should be able to find out first using equilibrium equation. Or you can draw something known as torque diagram, just like bending moment diagram. You can also draw torque diagram here. Let us try to write that. I'm trying to draw the torque diagram. Let us say this is my reference line, zero line. Now, in order to find out the effective torque, you have to come either from right hand or from left hand. Now, if you take a section at any location between C and D, when you come from right, wherever you take the section from right, the torque acting is 2 kilonewton meter. From D to C, the effective torque is 2 kilonewton meter, and it is acting in clockwise direction here. I will take it as positive, or you can take it as negative also. It is just a convention. I'll draw it here. What is this? This is 2 kilonewton meter. It is a torque from C to D. But as soon as you cross the section C, or if you take a section between B and C, then you have to take the effective torque between 3 kilonewton meter and 2 kilonewton meter, which are acting opposite in nature, and it becomes plus 2 minus 3, because we have taken clockwise movement as plus. This is anti-clockwise movement at C, it has to be taken minus. So 2 minus 3, it becomes minus 1. So I will draw here. From C to B, the same torque will be applied. This is minus 1 kilonewton meter. That is between C and B. As soon as you cross B, or if you take a section between A and B, then from right side you will have to take the effective torque of 3 torques. So plus 2 minus 3 minus 1. Plus 2 minus 3 minus 1. So it will be minus 2. So I have to draw minus 2 here. Minus 2 kilonewton meter. So this is known as torque diagram, which can give you the data of different effective torques that are acting at different sections. This is called torque diagram. We want to find out the total angle of twist here. Total angle of twist in the entire shaft is the summation of angle of twist in the portion AB, angle of twist in the portion BC, and angle of twist in the portion CD. It is algebraic summation of those angle of twist. And we are also supposed to find out the maximum shear stress in each portion, which depends on the torque applied at each portion. Diameter is given as D 60 mm. G is given as 8 into 10 power 4 megapascal. These two values are given to you. We also know that angle of twist theta is TL by Gj. Right? This is from the equation T by J. So from this criterion, I can write theta is equal to TL by Gj. And maximum shear stress tau can be written as T divided by, this is taken from tau by R. Tau is equal to T into R by J. Find out what is the polar moment of inertia. So for this shaft, J will find out 5 into D to the power 4 by 32. Comes out to be 1.2723 into 10 power 6 mm power 4. Now we'll try to find out angle of twist in each portion. Angle of twist in each portion. First, we'll apply to theta AB. Theta AB means angle of twist in the region AB. Now here we know the equation is TL by Gj. For the portion AB, T is nothing but minus 2 kilonewton meter. Minus 2 kilonewton meter, I'll convert it into Newton millimeter. So it becomes 2 into 10 power 6. This is the T value for the portion AB. Into length. Length is also given actually. I have not written here. I'll write that. This is 2 meter. This is 1 meter. This is 1 meter. So length also is known. Length is 2 meter for portion AB. So it is 2 into 10 power 3 millimeter divided by Gj. G is 8 into 10 power 4 into J. J is 1.2723 into 10 power 6. So this you have to calculate. Comes out to be minus 0.0393 radian. You can convert it into degrees also. Now we will calculate for the other portion, theta BC. Again it is TL by Gj. T for the second portion is minus 1 into 10 power 6. From the torque diagram it is clear. Into the length. Length there is 1 meter. It's also given in the problem. 1 meter is the length between B and C. 1000 mm. 1 meter is 1000 mm. Divided by G is 8 into 10 power 4. Into J is same, 1.2723 into 10 power 6. comes out to be minus 0.0098 radian. So we have found out angle of twist for portion AB and BC. Next is the last portion, CD, where torque is plus 2 now. So theta CD is plus 2 into 10 power 6 is the T value there. Into length is 1 meter there also, divided by G into J. So this, if you calculate, comes out to be plus 0.0197 radians. So we have found out angle of twist in each portion. That means third subdivision of the question is answered already. In order to find the total angle of twist, we have to take the algebraic summation of these three individual angle of twist. That is why I have taken this minus sign and plus sign as it is. So total angle of twist or net angle of twist, I call it as theta T, is theta AB plus theta BC plus theta CD, which is minus 0.0393 minus 0.0098 plus 0.0197. Just calculate that, so much radian. Then the second part of the question is maximum shear stress in each portion that we have to find out. Maximum shear stress the shaft is TR by J. First, let us try to calculate for the portion AB is T into R by J. T for the portion AB is minus 2 into 10 power 6 into R by J is same for all the cases. R is 30 mm and J is 1.2723 into 10 power 6. So into 30 divided by 1.2723 into 10 power 6. We have to calculate this, which comes out to be minus 47.2 megapascal. Shear stress in the region BC is minus 1 into 10 power 6 into 3 into 30 divided by 1.2723 into 10 power 6. To calculate this, you will get minus 23.6 MPa. Tau TD plus 2 into 10 power 6 into 30 divided by 1.2723 into 10 power 6 comes out to be 47.2 megapascal. So we have got the answer for all the three problems. So here the shaft is subjected to different torques at different sections. First you have to find out effectively how much torque is acting at each portion and then try to use the torque equation. That's all. And total angle of twist always will be equal to algebraic summation of all the individual angle of twists in each portion. Next, we will consider this problem. Shaft of 500 mm length and 40 mm external diameter is bored for a part of its length AB to a 20 mm diameter and for the remaining length BC to a 30 mm diameter bore. If the shear stress is not to exceed 80 Newton per mm square, determine the maximum power the shaft can transmit at a speed of 200 rpm. Also determine the length of bored holes. First, we will try to write the sketch for this. The shaft of length 40 mm initially. Try to draw the shaft here. This is the original shaft of diameter 40. Next, it is bored. He says it is bored. Bored means centrally hole is made. Portion AB to a diameter of 20 mm. Let us call it as A, some portion here B and C. The entire length has to be divided into AB and BC. AB need not be equal to BC here. We have to find out the length. For the time being, we'll write these 3 points like this. Now, how it is bored? It is bored for the portion AB to a diameter of 20 mm. Means there will be a hole created here. This is the hole created. This diameter is 20 mm. And for the remaining length of BC to a diameter of 30 mm. So beyond B, there is a different diameter. So let us say it is diameter like this. This is also bored only, but here diameter is different. This diameter is 530 mm. So now, since the central material is removed, it is actually a shaft of this kind. It's a hollow shaft now with different inner diameters for the portion AB and BC. If the shear stress is not to exceed 80 Newton per mm square, means tau is equal to 80 MPa. That's given. Speed of 200 rpm. Also determine the length of bored holes. Means I have to find out what is this length. Total length is given as 500 mm. And length of portion AB we have to find out. Let us say it is called as L1. And when we call that length as L1, the other remaining portion should be 500 minus L1. Here what we have to do is we have to find out the torque in the portion AB and BC, and whichever is minimum, that is the torque that can be transmitted through the shaft. Maybe the portion AB is capable of transmitting more torque because more material is there, but the portion BC is not so strong because less material is present. So the portion BC decides what is the amount of torque the entire shaft can transmit safely. So let us try to find out that. Torque equation is E by J is equal to tau by R, but this is hollow shaft, so I'll write R naught here. Or I can say E is equal to tau into pi D naught cube into 1 minus D naught power 4 divided by Di power 4 divided by 60. How I got this? I substituted for J. J is nothing but pi into D naught power 4 minus Di power 4 divided by 32. R naught is D by 2. So when I cancel D naught, I will get D naught cube here. I have taken D naught power 4 outside and cancelled 1 D naught. And 32 by 2 will become 60. Okay. If you want, you write one more step for this. This is the torque equation I have to use for different portions. For the portion AB, I will write pi by 16 as it is into tau is 80 into D naught cube. For the portion AB, outer diameter is 40. So 40 cube into 1 minus 20 power 4 here, 4 divided by 40 power 4. So this you can calculate. It comes out to be 942.5 into 10 power 3 Newton millimeter. Similarly, if I apply it for the portion BC, what it becomes pi by 16 into 80 into outer diameter is also same for the portion BC. But only thing is inner diameter changes. So 1 minus 30 power 4 by 40 power 4. This you calculate, it comes out to be 687.2 into 10 power 3 Newton millimeter. Now you observe TAB is 942 Newton meter, TBC is 687.2 Newton meter. Out of these two, TAB is more, means AB portion of the shaft is capable of transmitting this much torque safely. But BC portion, as the cross-section area is reduced here, it can transmit only 687.2 Newton meter safely. So overall, if you consider the entire shaft, the safe torque transmitted that can be transmitted is TBC1 687.2 Newton meter. This is the safe torque that the shaft can transmit. Now using this safe torque, I can calculate what is the power. Therefore, maximum power that can be transmitted is P is equal to 2 pi NT by 60,000, which is 2 pi into N is 200 here into T is 687.2 divided by 60,000. Observe that I am substituting T in Newton meter only. Okay, don't substitute in Newton millimeter. So you have to be careful in this equation. So if you calculate this, it comes out to be 14.39 kilowatt. So this is the maximum power that this shaft can transmit. Also determine the length of bored holes, means L1 and 500 minus L1. Those two things we have to find out. We know that angle of twist theta is equal to T into L by Tj. Okay, that's the equation for theta. But in this shaft, angle of twist in portion AB should be equal to angle of twist in the portion BC. So here theta AB should be equal to theta BC. TL by Gj of portion AB should be equal to TL by Tj of portion BC. Torque is same here, the entire shaft. So T and T can be cancelled. And material is also same, so G can be cancelled. Only L by J will be there. So L1 divided by J. J is pi into 40 power 4 minus 20 power 4 divided by 32 here is equal to this. I'll call it as L2 divided by L2 is nothing but actually 500 minus L1. We'll substitute that. J for this portion becomes 40 power 4 minus 30 power 4 divided by 32. So the inner diameter is 30 here. So this, if you calculate, you'll get L1 is equal to value into L2. That's what you get here. But we know that L2 is equal to 500 minus L1. So equation 1 and equation 2 can be solved. This will give you the value of L1 and L2. L1 you are supposed to get 210.84 mm and L2 will be obtained as 289 mm. Just try to calculate this and see whether you get these answers. Then this is a problem for homework. It is a solid shaft of 60 mm diameter which has to be replaced by a hollow shaft of the same length. The outer diameter of the hollow shaft is same as that of solid shaft. If the angle of twist per unit torsional moment is same in both cases, determine the inner diameter of the hollow shaft. G of hollow shaft is equal to 3 times the G of solid shaft. That's the given condition for material. The answer is 54.2 mm. Angle of twist per unit torsional moment. This is nothing but angle of twist is theta. Per unit torsional moment means divided by t. Is same for both the cases means for solid shaft is equal to theta by t of hollow shaft. You have to utilize this condition and find out what is DI required. Solid shaft diameter is 60 mm and the hollow shaft also has the same outer diameter. So DO is also 60 mm. DI you have to find out.